Hello everyone, welcome back to Simscope. Today I'm going to talk about a project titled Design a Power Converter for an Industrial DC Conveyor Motor. In this video, I'll walk you through a design and simulation of single-phase AC to DC buck converter fitting a DC motor built completely in the MATLAB Simulink. We will start by understanding the Simulink model first, then analyze the simulation results, and finally discuss future improvement and real-world applications. This project is suitable for power electronics, for motor drive, and uh, a final year engineering students doing the project. Firstly, let's see the project overview. The background says a small packaging workshop in Perth operates a DC conveyor belt system, and they use a DC motor of DC motor, and that needs to be controlled. So the objective of this project is to firstly convert 230 volt single phase AC supply into a controlled DC voltage and use it to regulate the speed of a separately excited DC motor. The system consists of three main stages. Number one is AC to DC rectification. Then second stage will be DC to DC buck conversion using PWM, and stage 3 should be DC motor drive using the armature voltage control. Okay, here are the detailed talks of the project, and I will skip this part and let's directly move on to the uh, Simulink model. Firstly, the AC input stage we have here is the input. We are using 230 volt phase voltage in the RMS value, and when we find the peak voltage by multiplying root 2 into the phase voltage of 230, we will get 325 volt, and it represents a sinusoidal voltage source, which is described by this equation. The peak voltage of this voltage is root 2 times 230, which is 325 volt, and as you can see, now we will finally confirm this voltage using the scope. Now, rectifier and a DC-link. A AC voltage is then fed into a single phase diode bridge rectifier, which converts it into a pulsating DC voltage. To smooth, we are using four numbers of diode, two in series, and they are connected in parallel to each other, and this forms a single phase bridge diode rectifier. Then the output from the diode is given to a capacitor number C1, and the value of a capacitor is 1000 microfarad. To smooth This voltage from the rectifier, this DC-link capacitor of 1000 microfarad is connected across the rectifier output, and on the DC-link voltage waveform uh, here V1, we will observe a startup changing transient followed by the steady voltage of around 316 to which varies. Yeah, however, we are getting an output voltage across the capacitor around 316 volt. In calculation, it should be around 325 volt theoretically. And we then next we have a buck converter. Firstly, one IGBT which have a gate pulse from the gate pulse generator here. For the buck converter, we have an inductor of 3 microhenry and another capacitor C2 of 2200 microfarad. Then a diode is D5 is connected as shown here, and finally its output is connected to the armature of the motor. The buck converter will step down the high DC-link voltage. This is a DC-link voltage V1 to a lower and controlled DC voltage suitable for the motor. The converter consists of, as I showed, all of these diodes, IGBTs and capacitors, and uh, this slider switch is used to control the pulse width modulation or PWM, and the output voltage uh, given to the armature is the V2, and this V2 is equal to the duty cycle T times this voltage. So sorry, the output voltage V2 is equals to duty cycle times V1 input voltage. So this means by adjusting the duty cycle, we can control the motor's armature voltage. By controlling the motor armature voltage, we can control the motor's speed. Now, if we go to the PWM generation side, we have a constant block which is connected to this slider, and slider is used to make the duty cycle variable. This slider have a duty cycle range of 0 to 1 at the step of 0.1, and by increasing the duty cycle from 0 to 1, we are going to increase the speed gradually. The PWM signal is generated by comparing this triangular carrier waveform with a constant duty cycle reference, and this is the repeating sequence time value and output values as shown. When the carrier is lower than the reference duty cycle, this IGBT switch will turn on, and when the when the carrier is higher than the duty cycle, then it will turn off this switch. By switching on and off, we can control the output voltage going into the motor. Now let's go into the DC motor model. I am using a DC machine. The load used in this project is a separately excited DC motor, which is ideal for armature voltage spread control. The field winding is supplied with a constant DC voltage, keeping the magnetic flux constant. This is done by connecting it to a battery of nominal voltage 48, rated capacity of 10 Ah, and its initial state of the battery charge is 100%. The battery response time is 30 seconds. The motor, it takes an input mechanical input in torque, and its field type is wounded type. So the other parameters of the motor given in the project question is as given here. The armature resistance and armature inductance are 0.6 and 5 microhenry respectively. Field resistance and inductance as given here. The field armature is the 1.8. Then initial speed of the motor should be 0. And I am applying 3 Newton meter of uh, mechanical load, which will represent the conveyor's load. Now for collecting the data, we have VIN, which is collecting the input. Sorry, this should be VIN. This is measuring the AC voltage or voltage across the source. Then V1 will measure the voltage across the DC-link, rectifier DC-link. Then the output voltage will be measured by V2. This voltage is a voltage applied across the motor, and these informations are given to a scope that we will analyze soon. Then using the bus selector, I have my other informations from the motor, like speed of a motor, armature current, field current, and torque from the motor output. Now I have already simulated. Let's see what happens at the duty cycle of 0.3 and see the result. Now, okay, we have 3 waveforms. First is a input AC waveform, and this top load input AC waveform is a clean sinusoidal waveform. and its peak is uh, its range is plus or minus uh, 325 volt. No distortions are there. It is a ideal AC source. So this confirms that our input is correct. Then next, at the DC link, the DC link voltage V1 is V1. What you see is a large oscillation at the beginning. Then it settles around 310 to 325. So it settles within 310 to 325 range, right? And there's a small ripple, and you can see that this AC voltage is now converted into the DC voltage at a steady state. This happens because of the transient period. At the startup region from around 0 to 0.12 seconds, the DC link capacitor starts uncharged, and it charges through the diode bridge. Each AC peak charges the capacitor higher. This causes a very large ripple pulsating voltage, and this is a classic capacitor charging transient. It is unavoidable and 100% realistic. Then at the steady state from 0.12 after 0.12 seconds, the capacitor is fully charged and it discharges slightly between rectified peak. It recharges every half cycle at 100 hertz. This causes a small ripple at twice the supply frequency, you can see, and the average DC link voltage near this peak AC is around how much? Is around 318.9 volt. Okay, now let's see the buck converter output. Output from the buck converter, or the V out, is given in the bottom plot. This is the most interesting one. We can see at the stage 1, while initial rise and there is an oscillation from 0 to around 0. How much? 0.1 second, around here, somewhere 0.02, 0.03 seconds. So what you see is a fast voltage rise, right? And there is also an oscillation and a ripple, and there is undershoot and overshoot. Why this happens? At the startup, inductor current starts from 0. Then this starts from 0. Then the output capacitor is initially uncharged. The PWM suddenly applies chopped high DC voltage, and this causes the LC resonance, inductor plus capacitor. There is a high inrush current and voltage shrinking. This is an open loop system, so nothing to damp it instantly. Therefore, this transient feature is expected. Then there is a from 0.25 you can see that there is an overshoot. The output voltage rises above the final value. This is the final settled value, and there is an overshoot over here, which its peak is around 165, 60. Anyways, it starts from 165 to something 7 year. Why this happens? There is three reasons. Number one is LC energy storage. The inductor stores the energy faster than the motor consumes it. And number two is a motor's back EMF. As the speed increases, the back EMF reduces the armature current. So less current, there is less voltage drop, and you can see the voltage rise in this period. And third is as I said, there is no feedback control. So buck converter do not know the highest voltage it has, so it will just keeps on increasing. And this overshoot is expected in the open loop drive. Now at the stage 3, once it is dropped and in the settling period, what you see is now you have uh, a voltage gradually which is decreased here, gradually decreasing, and it settles at uh, around the range of 135 to 40 volt, right? Why this happens? Now the motor reaches at a steady speed, then the back EMF is stabilized. Armature current and torque balance load. I mean the armature current and torque balance the load torque. Then the LC filter stops exchanging the excess energy. So system, now we have reached the system in the electromechanical equilibrium. At the steady state, we can see a very small ripple. Now this is a DC voltage, and the inductor is producing a smooth current. The capacitor will smooth the voltage. Inductor will smooth the current, and motor act as a low pass filter, and therefore uh, the ripple is attuned. You can see that the output ripple is less than 5%. Now these are some of the important things. Now let's see what are the results um, at the motor side. Motor side, the speed is currently 70.35. Then the DC-link voltage V1 is 318.9. The output voltage is 135. So less than the rectifier voltage, DC-link voltage. So V1 should always be less than I mean V2 should be less than V1, and at the duty cycle of 0.3 we get the speed of 3.5. Then the armature current we are applying, or the circuit current here is 1.74. Then The field current is 1.06 amps and the torque is 3.32. Now, as per this performance, we can say that the converter provides a high efficiency, simple control. And in the industrial settings, such power electronic controller is very simple to construct. It is going to cost, it's cheap, and it is reliable in controlling the speed of a motor. Such circuits will be further can be used in uh, the other applications would be like a battery charger. Maybe you can use it in a DC power supply, electric as an electric vehicles auxiliary system. Then it can be also used to drive the motor as shown here. So finally, we could conclude that the project demonstrate a design and simulation of the a single phase AC to DC buck converter for industrial DC conveyor motor. And finally, I would like to show you one more thing. Let's change the duty cycle, increase the duty cycle, and see if we can change the speed. I don't need this one for now, so we increased to 0.5. So now we are getting an increased speed, motor speed of 300, 300 something. Okay, it is. Okay, now while we increase the duty cycle from 0 to gradually increase from 0 to 1, the speed should increase. At the 0.3 motor speed was 70, so 0.5 motor speed has increased. And if you observe the waveform, you can now see that there is a more transient formed, and there is more overshoot, and you require more time to settle your motor behavior in a steady state. So it takes that the settling time, it takes the motor, or the settling time for the motor is larger when we increase the duty cycle. That's the disadvantage of such circuit. Thank you for watching. If you found this helpful, please like, subscribe, and comment, and check out my channel for more Simulink and power for engineering projects. I am going to upload the file, this Simulink file, and the related documents in Gumroad. You can check my check in the description or check my bio for the link, so that you can download this MATLAB file and you can use in your projects. Thank you.